The second conservative force to discuss is the elastic force, also known as the spring force. So we abbreviated F subscript little s. Here's a spring. It's attached to a wall at the right end. Its left end is going to be free to move, and we'll note the location of the left end by the coordinate x. Initially here, the spring is at its natural length, neither stretched nor compressed, and we've got incoming a cart with some kinetic energy. It looks like 6 units of kinetic energy, and you'll see that throughout this story, the total energy in the system remains 6 units, just what the cart is bringing in. Some of that energy is going to be transformed into what we call elastic potential energy. That'll be the energy stored in the spring when we compress it. And we represent elastic potential energy with U subscript little s, big U, little s, US, elastic potential energy. So a moment later, the cart has run into the spring and begun compressing the spring. The spring is, of course, pushing back on the cart, so that's represented by Fs here. This is the force exerted on the cart by the compressed spring. We see that the cart has slowed down, comparing its initial incoming speed to now, and the location of the left end of the spring is being given by this x coordinate here. The spring has compressed this distance. So x is the displacement of the spring from its natural unstretched position. So we're going to call this a positive x when it is displaced to the right of its natural unstretched position. And so this spring force pointing to the left, we see has been doing negative work as the spring compressed. Comparing the spring force to the velocity, they're 180 degrees apart. So the negative work being done by the spring force on the cart is this guy right here. Here's our spring force transferring the kinetic energy of the cart into spring potential energy or elastic potential energy represented by these red orbs here. So removing kinetic energy, turning it into spring potential, storing that energy in the coils of the spring as it compresses. Now the cart will come to a moment where it has maximally compressed this spring, and then it will rebound and head back to the left. So here's that moment a short time later. Now the spring is pushing back on the cart or moving the cart back to the left. So the cart is now speeding up, heading towards the initial equilibrium position of the spring. There's our spring force on the cart at that moment. And comparing these two moments, we see that when the spring is more compressed, it's exerting a bigger spring force. Here it's less compressed, it's exerting a smaller spring force. That's a key feature of the spring force. The magnitude of it varies with the degree to which the spring is compressed or stretched, as we're about to see. The spring still has a positive displacement at this moment. That's the x value here. And the spring is now doing positive work. Look, the spring force is in the same direction as the velocity. So that positive work means that the spring force is now converting some of that temporarily stored spring potential energy back into kinetic energy, speeding up the cart once again. So from the initial time to here, we've had kinetic energy converted into spring potential energy as the spring compressed via negative work done by the spring, and then converted back into kinetic energy via positive work done by the spring. Beyond that point, let's suppose that the spring attaches to the cart. Maybe there's a magnetic clamp there that holds it onto the cart, so that when the cart passes this x equals 0 position, it actually pulls the spring out with it, stretching the spring. And when that happens, the spring, of course, is going to be exerting a force on the cart backwards to the right, trying to pull the cart backwards as the spring stretches out. So here's that spring force on the cart as the cart travels off beyond the x equals 0 location. We'll say that the displacement of the left end of the spring, what we're calling x, is now a negative number over here. We're displacing to the left of equilibrium, so x is a negative number. The size of that spring force is going to depend on how much the spring is stretched. So comparing the spring forces here and here, we see that this small compression results in a smaller spring force than this large extension. Bigger spring force here, given that the spring is extended to a greater degree than it is compressed at that moment. And here the spring is doing negative work, slowing the cart down, transferring its kinetic energy into spring potential energy once again. So the spring can store energy either when it's compressed, take kinetic energy, turn to spring potential energy, or elastic potential energy when it's compressed, or when it is stretched. It's also storing elastic potential energy now. There will come a moment when the cart comes to rest, when the spring is maximally stretched, and the spring will then pull the cart backwards to the right, reversing its direction of motion. So here's that moment as the cart is now traveling to the right once again, being pulled by the spring. The spring is not as stretched in this moment. Compare the displacements, the x values. It's not as stretched in this moment as it was in this moment, and so the rightward spring force is not as great at this moment as it was at that moment. The spring is now doing positive work, so it's speeding up the cart once again, transferring the stored elastic potential energy back into kinetic energy. And so we'll summarize this relationship by noting that the work done by a spring force equals the opposite of the change in the elastic potential energy stored by the spring. And that's either when compressed or stretched. Let's talk about that minus sign for a moment. Note in these situations above that whenever the spring is doing negative work here and here, it's removing kinetic energy and increasing the spring potential energy. So when the spring does negative work, US increases. When US increases, the spring does negative work. Likewise, when the spring does positive work here and here, spring is doing positive work, it's converting stored elastic potential energy back into kinetic energy. So US is decreasing when the spring does positive work. So when delta US is negative, negative times negative gives us positive work done by the spring. That's the meaning of the minus sign there. And that's going to bring us to the topic of solid mechanics. Here's a little bit of solid mechanics 101 here. Some principles about how to mathematically model a spring. All solid bodies will deform under stress. Deform means change shape, either by compressing or stretching or flexing or twisting. All solid bodies will deform when you stress them. Stress means an applied force or an applied pressure. And there are three response behaviors when subjected to stress. Elasticity is when a body returns to its original size and shape once the stress is removed. It rebounds back to how it was once you remove the stress. That's elasticity. Think of an elastic rubber band. Plasticity is when a body is permanently deformed by stress. So think of taking a paper clip and bending it so much that it stays bent. When a bent thing stays bent, that's plasticity. It's behaving in a plastic manner. It's not rebounding. It's remaining permanently deformed by the stress. Then there's brittleness, and that's when a body fractures under stress, when it is deformed to such an extent that it breaks or cracks. Most materials are going to respond to increasing stress like this graph shows here. Here we have stress graphed against strain. This is a stress versus strain diagram showing the stress applied to a body, that's like the applied force, as a function of how much strain or deformation the body undergoes. So to illustrate this, I've got our miner here pulling on the handle of his pick, applying a force to the handle, and we see the handle is actually bending here because of how much force he's applying. So the miner is applying a force, and the bending of the handle is the strain. The more the handle bends, the more strain it's exhibiting. Now the handle and most materials are going to exhibit a spring-like elastic behavior when subject to relatively small applied forces, relatively small stresses. That is, the strain will increase linearly with the stress, this linear relationship here. So when you double the applied force, you should double the strain. That is, get twice as much bending or flexing when you double the force that you're pulling with. Now, of course, that only holds up to a limit. The handle here is likely to rebound back to its original shape when the miner lets go, unless he pulls too hard. If you apply enough stress, you could permanently bend that handle. And that's when you've transitioned from this elastic regime to the plastic regime here. Apply enough force, and you're going to bend that handle in such a way that it does not rebound. It's going to bend so much that it stays bent. That's plastic behavior. That's an irreversible strain here. It stays bent. And if you continue to apply even greater stress beyond the point where the material has become plastic, where it's bending permanently, you could get to the point of fracture here. There will be a breaking point that's sort of a maximum stress that you can apply, a maximum force you can apply to the object before it just straight up cracks or fractures or breaks. And that's what we've got here in this final depiction here. Suppose you bent the handle so far, it became plastically deformed, and then you kept turning it over, and it just cracked right there at the most stressed point.